of course, when Newton was inventing calculus, he was doing it for the sake of supporting his own theories about the laws of motion and physics. But many other mathematicians quickly realized that this has applications that are far beyond just the realm of motions and physics. And so we just want to talk about that in a more general sense, because we can talk about it in terms of the net change in quantity over time. The important part of all of this is to keep track of your units that are associated with your quantities and your rates involved. Because if you take the integral of the rate of change, you will have the net change, right? Just like the displacement, right? So this would be the displacement in cost, or it could be the displacement in quantity, or it could be displacement, right? Displacement, even though we've used that term for meaning, well, the net change in distance, it can mean more than that. And so that's what we're talking about here. So the net change in that quantity, right? Right there. Now, a frequent application of this is cost, but it's not the only application. There's actually lots and lots and lots, infinitely many applications, but a frequent one is cost. Now, keep in mind that marginal cost is the derivative of cost. So if you wanted to know the change in the net change in cost over time, you would need to know the rate of change, i.e. the marginal cost, and then this would work, right? So that's another item for you to keep track of. Okay, but we're not going to do a cost one just for the heck of it. We're going to do a cistern. So we have a 2,000 liter cistern. A cistern is a big tank that holds water, oil, whatever. This one particularly holds water. Just for the sake of it, I thought I'd Google it so you guys can see what a cistern looks like. You can actually buy ones in more rain-parched areas that connect to your rain gutters and such. But these are ancient cisterns that used to hold water. So they're fascinating to go see in Europe where they hold water, but they're big tanks essentially. You've got a big tank that's holding water. That's what it is, right? So we have a tank, a 2,000 liter tank that's holding water. It's empty when it's not holding water. It's empty, and water begins flowing into it at a rate in liters per minute given by q prime of t equals 3 square root of t, where t is measured in minutes. Interesting. Okay, so notice, by the way, that they're telling us that it's empty at the start. So they're telling us that the quantity at time 0, or q sub 0, is 0. Good to know. All right, they want to know how much water has flown into the cistern in 1 hour. Okay, so for part A, they're really asking us what's the net change in water over the first hour. That's what they want to know. Okay, well, that net change, according to our net change theorem here, very nice to know. Matter of fact, I should highlight it, right? This is basically saying, hey, all that stuff with distance and displacement, it works with anything, right? Anything that you know the rate of change for. All right, so that means that if I want that net change would be equal to the integral from a to b of the derivative of q, aka q prime, which is equal to the integral. Now I want to know for the first hour. Tricky. Now you'll notice they gave it to us in minutes here. T is measured in minutes, and then they say hour. So that's tricky. They're saying from 0 to 60 minutes. All right, so I'm going to go 0 to 60 right here. And then it's 3. And I'm not silly enough to write a square root, so I know that's a 1/2 power, so I'm going to do that because I'm going to have to take the integral of this thing, which is the integral from, it's 3 times 2/3 t to the 3/2 from 0 to 60, which is equal to 2, because of course the 3's disappear there. So it's 2 times 60 to the 3/2 minus 0 to the 3/2. Okay, so 2 times 60 to the 3/2, we can make this happen. Come here. All right, 2 times 60 to the 3 halves. It's about 929.516. What? Well, it's how much water. So that would be liters, right? Because the flow rate was in liters per hour, or excuse me, liters per minute, right? So it was liters per minute. So when I integrate over minutes, I'm left with liters. That's why they're saying you want to pay attention to the units associated and the rates involved, right? So as long as I pay attention to the units, I'm good. So 60 minutes, right, because it's minutes, and then it was liters per minute, so therefore it's liters. All right, next, they want us to find the function that gives the amount of water in the tank at any time t. This is no problem. Okay, so B, they want us to find Q of t. Okay, well, Q of t would be the integral, the general integral of Q prime of t. That's the fundamental theorem of calculus, right? Fundamental theorem that we learn in Calc 1, I'll call it FTC, fundamental theorem of calculus, is that the function is equal to the integral of its derivative. In other words, derivatives and integrals are opposites of each other. They're inverse functions of each other, for lack of a better term. So this is the integral of 3t to the 1/2 dt, which we already did. Here, let me do it this way. We did it up above. It's 2 times which is 2 times t to the 3/2 plus c. Now, that's the general solution. It's not the particular solution, but that's the general solution. We need to find the particular solution, so we need to solve for c. So we need to use the fact that q of 0 equals 0 to solve for c. Well, this is going to be really easy because if I put 0 into there, right, 2 times 0 to the 3/2 plus c is equal to 0, which means that this is all gone, c is equal to 0. Therefore, q of t is equal to 2 times t to the 3/2. Done. But of course, we're not done with the whole problem because now they would like us to graph q of t. Okay, so let me rewrite it. Q of t was equal to 2 times t to the 3/2, right? So that's q of t. All right, so let's go graph it in Desmos, shall we? I think this is this example right here. There it is. So 2 times, I did x, I mean, either one. So 2 times x to the 3/2, there you have it. So I'm going to draw a graph. And you can see that I'm going out to a scale of about 120, and it's starting off at 0, and then it kind of swoops up. Okay, so, and then this is at a height of, it looks like 2,500. So I'm, of course, going to draw all of that on the scale. I at least have to give it, you know, a little bit of scale here. So that's 0. This is q of t equals 2t to the 3/2. There we go. And it keeps going like that. All right, so we graphed q of t. I mean, what more is there to say? Not much. All right, so that's part C, all done. And we made sure we had some scale in there. That's lovely. And then the last part is they want us to know when the tank will be completely full. So when will tank, when will tank be full? Okay, full. Full would mean that q of t, which was 2t to the 3/2, is equal to 2,000, right? Because it said it was a 2,000 liter tank. So solving this for t shouldn't be too difficult. We divide both sides by 2. We get t to the 3/2 is equal to 1,000. So t is equal to, of course, if you want to get rid of the 3/2, You raise both sides to the 2/3 power. This will disappear, right? Those multiply into nothing, into 1 actually. So t to the 1 is equal to whatever 1,000 to the 2/3 is, which is 100. I mean, if you don't believe me, you can go check it in Desmos. But the cube root of 1,000 is 10. 10 to the 2 is 100. So it's 100 minutes. That's when it will happen. Or if you want to think of it this way, it's 1 hour, 40 minutes, right? Now I can tell that I'm right. I can verify with the graph. So if I look at my Desmos right here, I can see right here that these, I put in a graph of y equals 2,000, and sure enough, it's equal right there. Oh, and look, I did 1,000 to the 2/3 right there, and it's 100. I did it in my head as well, but it all works out. You'll notice, by the way, that if you wanted to check yourself in terms of finding the integral, I did that right here. It doesn't count as by hand work, but at least you can check that the 929.51 that we came up with in the original part A is correct. All right, so I can make a little note right here. You can tell that my graph is really not to scale, but I can notice that I've verified. And there we go.